Thank you everyone for coming to this talk. So in this talk, I will talk about inapproximability of VC dimension and little stones dimension. This is joint work with Aviad Rubinstein, who is also from UC Berkeley. And to fit this talk into 10 minutes, I will focus on the VC dimension result and not touch too much on the little stones dimension result. I will touch on it a little bit at the end. So the main question that we try to study in this paper is the computational complexity of computing VC dimension. So in particular, given a universe or a ground set U and a concept class C, we want to determine the VC dimension of the concept class. And it turns out that the computational complexity of computing VC dimension, or approximately computing VC dimension, actually depends on how you model the input. So let me tell you what the representation of the input here. So in our case, in our work here, we consider the case where the input is given to us as a matrix. So it's just a matrix where the ij entry is 1 even only if the ith element is contained in the j concept. So note that the size of the input here is the size of this matrix. So just the number of elements times the size of the concept class. And the first observation about this representation of the input is that the problem can be solved in n to the O of log n time. This is just because the VC dimension is at most log of the size of the concept class. So we can actually enumerate all the subset of elements of size at most log n and then check whether it's shattered. And this can be done in n to the O log n time. However, we don't know any polynomial time algorithm for it. So this puts this problem in kind of this strange complexity class where we don't know polynomial time algorithm for it, but it's also unlikely to be NP-hard, because if it's NP-hard, then the whole NP is contained in n to the O of log n, which is perhaps unlikely. So in an attempt to prove hardness for this problem, Papadimitu and Yannakakis show that the problem is log NP complete. And you don't have to worry about the exact definition of log NP complete, but one thing I would like to point out here is that if you assume the exponential time hypothesis, or ETH, which I will formalize in the next slide, then the result implies that you cannot compute the VC dimension exactly in times much less than n to the log n. So in n to the O of log n time, you cannot compute the VC dimension exactly. But that result doesn't rule out approximation algorithms. For example, it could be that there is a polynomial time algorithm that approximates VC dimension to within, say, a 1.1 factor. This wouldn't contradict with that result. So in this work, we rule out these kind of approximation algorithms as well. So we show that if you are only allowed to spend much less time than n to the log n, then you cannot get any good approximation algorithm. And here in this work, we can prove the inapproximability ratio to anywhere less than 2. But let me note here that this factor of 2 is kind of arbitrary. This is just because our proof doesn't work for the factor beyond 2, but it's totally possible that with some other technique you can go beyond factor of 2 here. So that's the setting. So let me tell you about the exponential time hypothesis, or ETH. So one formulation of the ETH is just that there's no sub-exponential time algorithm that can solve the tree coloring problem. So given a graph G, you actually need 2 to the some constant times n time to decide whether G is tree colorable. And how can this help us in proving hardness of approximation? So this brings us to the framework of Aronson et al., which is sometimes called the birthday repetition framework. So in this framework, we start with a tree coloring instance. So we want to decide whether graph G is tree colorable. And assuming ETH, we have exponential time lower bound on this problem. In the first step of the framework, we apply the PCP theorem. And for the purpose of this talk, just think of the PCP theorem as producing another graph G prime, where in the yes case, the G prime remains tree colorable. But in the no case, not only that it's not tree colorable, but every tree coloring actually violates many edges, at least 1% of the edges, say. And note here that there is like a gap here, because in the original case, it's possible that in the no case, there is some tree coloring that violate only 1 or 2 edges. And by now we know that the PCP theorem, that there is a nearly linear size PCP theorem in the sense that the graph G prime can be made to have size at most linear in the size of the graph G. So this n prime here is still roughly n, where there is some polylog factor that I hide in there. So the lower bound on the running time is still exponential here. And then in the second step of this framework, we reduce this into our problem at hand. And in this case, we reduce it to VC dimension. And the size of the reduction will be something like 2 to the square root of n prime. And let me note here that when the size of the reduction is 2 to the square root of n prime, then for this new big N, the big N to the log of big N is 2 to the square root of n prime to the square root of n prime. So this is why we get the low bound of n to the log n here. And in the yes case, we want VC dimension to be large. In the no case, we want VC dimension to be small, so that we have some gap and we indeed get hardness of approximation. And so this second part is our main contribution, so let me say a few words on it. So we want to reduce gap coloring, tree coloring problem to VC dimension. So in the first step of the reduction, we will partition our vertex set V into square root n parts of equal size. And the universe is very simple. So the universe is just all the partial colorings to each partition. So for example here, coloring U1 red and coloring U2 blue is a valid partial coloring for this the first partition. So this is one element of our universe. And let me note here that since there are only root n partitions and each partition has size at most root n, the number of elements is at most root n times 3 to the square root n. So we are good in terms of the size here. And now we have to specify our concept class. And to not burden you with all the notations, I will not write it out explicitly, but let me just tell you what is the idea behind the definition of the concept class. So I will do this through looking at the proof for the yes case and the no case. So in the yes case, we have a valid tree coloring for the graph. So let's say that this coloring is called sigma. And then the intended solution, the set that we want to be shattered here, is the set that contains all the restriction of this valid coloring to each partition. So there are root n partition here, so we will have that the VC dimension is at least root n. On the other hand, in the no case, we want to prove that if every tree coloring violates many edges, then the VC dimension cannot be large. So here we would like to prove it by, let's say, by contrapositively. And so suppose that we have a large set that is shattered. We want to get back a tree coloring that doesn't violate too many edges. And note that since our elements are just colorings to each partition, if there is a large set that is shattered, then that large set already gives us some sort of coloring to almost the whole graph. However, the problem is that this coloring may violate too many edges. And indeed, the way we define the concept class is in such a way that it checks that the coloring doesn't violate too many edges. And that's pretty much all I can tell about the reduction in this talk. So let me conclude here. So assuming ETH, we show that there's no algorithm that run in n to the log n to the 1 minus little or 1 time that can approximate VC dimension to factor beyond 2. We also show a similar result for little stone dimension, but the factor that we get is not 2, it's just some constant. And of course, two obvious open questions are whether these approximation ratio, inapproximability ratios can be improved to maybe some larger constant or even every constant. And as far as I know, there's no non-trivial algorithms for neither of the problems. So it would be nice if there's a non-trivial algorithms for the problem. And since this is a complexity of learning session, I guess it's mandatory for me to talk about it a little bit. But unfortunately, we do not know of any implication of our result along this line yet. So our result doesn't really rule out any kind of efficient learner, unfortunately. But one implication of our result is that is in the little stone dimension case. So recall that little stone dimension correspond to an online learning setting, and in this setting, if we are given a black box access to an optimum adversary, then we can actually query it only polynomial number of times and compute little stones dimension exactly. So this means that the optimum learner cannot be polynomially bounded. Otherwise, we can compute little stone dimensions exactly in polynomial time. So this means, in some sense, that the adversary cannot do his task in polynomial time. That's it for my talk. Thank you for your attention.
So, any questions? So, yeah.
Is there any hope for getting super constant approximability?
There is no particular barrier for getting it. Yeah. No. So actually, the best algorithm that I know is just you try to enumerate. Yeah.
So a while ago, I don't know, maybe 10 or more years ago, there were some results, if I recall correctly, for interapproximability of concisely described VC dimension instances, by humans, meant for humans and others. I was wondering if there's any connection in the methods or the approximation factors.
Yeah, so actually I'm not aware of that result, but there is another result on hardness of approximation for VC dimension, but in the case where instead of the input being represented as a matrix, it's represented as a circuit. So we feed in the index of the elements and the concept class, and it outputs 0 or 1, whether it's inside. And in that case, it's actually very hard. So it's sigma 3p hard to approximate to a factor of 2. But like 2 that appear there and 2 that appear here are for different reasons. But 2 that appear there is very interesting. There is an AM algorithm that approximates it to a factor of 2. So in some sense, that's kind of tight in that setting. But yeah.
Oh, any other questions?
So, let's see. I was just trying to think of just the connection to learning. I guess one thing that seems peculiar is if you had access to, say, a particular distribution of data, and you cared about how hard is learning for that distribution, then you could take some random samples, check to see if they can be shattered.
Mm-hmm.
It's like you say you had unlabeled data, right? You take the sample, see if they can be shattered. If so, great.
Yeah.
If not, then maybe you don't care if the VC dimension is high, because with respect to the distribution you have, it's not shattering. It seems like a peculiar thing that the hard case is when there exist these points that can be shattered. It's really hard to find them, right? So it's kind of interesting.
Yeah, I have to come clean here. I don't know much about learning, but yeah, it does seems like it's not that clear to me what the connection is. Yeah.
Okay, so I think you can thank all the speakers of this session.